Welcome. Today we're going to talk about eliminating code coupling. We're going to start by focusing on understanding and identifying coupling, recognizing bad coupling, and then practical decoupling implementations. We're going to cover these skills in coupling: what is coupling, when coupling matters, the types of coupling, recognizing bad coupling, code-to-code coupling, library-to-library coupling, and then practicing our skills on decoupling. So let's start with understanding and identifying coupling. First, let's get past some definitions. A dependency, it's a list of external requirements for one piece of code to build and run. Coupling is a direct dependency on an external requirement. Decoupling is an indirect or abstracted dependency on an external requirement. The key there being abstracted, it's not direct. So skill 1, learning when it is coupled. Code coupling is really limited to two important times for the code: compile time and run time. Now there's multiple run times. You can run your code in production, but you might just be running it in a QA environment or for integration tests, or you might just be running unit tests where you're not actually running your entire product, but just a small unit of your product and testing it. It's important to distinguish between these three because it's compile time coupling that is usually the problem. So there's many types of coupling: class-to-class coupling, library-to-library coupling, exe-to-library, temporal coupling, knowledge coupling, file folder coupling, external system, and convention. So as you look, we've marked which of these are mostly good, mostly bad. As you can see, coupling usually is bad. Class-to-class coupling is almost always problematic in code. Library-to-library coupling usually leads to spaghetti dependency chains, whereas exe-to-library, notice that's good. That's exactly how things are supposed to be. Temporal coupling, that means that some piece of code must run before another. That's time-based. Something has to run in a certain sequence. Knowledge coupling is where you are coupled to some bit of knowledge that you probably shouldn't have. File and folder coupling can be good or bad. You can be coupled to the existence of a file or a folder. That's not always bad. For example, in Visual Studio, we build to the bin debug, bin release. We're coupled to those, but that's not bad. But there are lots of bad file and folder coupling. External system, are you coupled to a web server, a database server? And then convention coupling, very similar to file and folder. The convention for Visual Studio is to build to the bin debug directory or the bin release directory, and now with .NET Core, the version directory. That's a convention, and it works really well. And so conventions can be good or bad. It's important to distinguish these so that you can understand which of these are more often problematic. As you look, it's the top two: class-to-class and library-to-library coupling. So that's what we are going to focus on. What we've learned so far: what is coupling, when coupling most often occurs, and different types of coupling. Now we want to recognize the bad coupling. As you saw in the previous screenshot, class-to-class and library-to-library were the couplings that we're calling bad. By bad, we mean it just usually leads to problematic code, difficult to maintain code. It doesn't mean that you can't use them or that your code's going to crash. If you do, it just means that you're going to pay a huge cost in maintenance, in spaghetti, dependency chains, and different things like that. And if you can avoid those, you'll save a lot of money in development costs, you'll be able to move faster, and your code will be more stable, more maintainable. So let's start by talking about class-to-class coupling. So what is class-to-class coupling? It's when any class references another class. So here's an example. Class A references class B. Here it's referencing it in a constructor. It could also be referenced in a method. Anytime you see class A calling a new class of some other type, you are coupled. That is class-to-class coupling. It's easy to recognize. It's pretty much anytime class A references class B. Now there are exceptions. You're really not coupling. You are coupling yourself to string if you use string. Same with int, long, right? You're coupling yourself to them. But is that bad? No, it's not. Primitives, simple models, those are exceptions. You can also say things like list. There's lots of things where you're just not going to have a problem coupling to those classes. Static classes force coupling and therefore are almost always bad. Exception, very simple statics like string.concat. If you're not simple like string.concat, just don't be static. Avoid it. And saying Microsoft wrote it does not make it okay. Lots of different skill levels between thousands of developers at Microsoft. Not all of them are writing the best code. Just because Microsoft wrote it doesn't mean it was written correctly. All right, doing it right. So when we talk about solid, one of the common phrases they say is depend on abstractions, not concretes. In a language like C#, abstractions are really interfaces. Yeah, you can have an abstract class, but let's just stick with interfaces. You'll be much happier if you do. So here you can see it's the exact same code as we were looking at before. A still depends on B, but it doesn't directly depend on B. It depends on an interface of B. Much better. That's it. It is that simple to fix class coupling. Depend on an interface instead of a concrete. So basic implementation steps in C# to remove class-to-class coupling. Use interfaces. Yes, for all classes. Use dependency injection and inversion of control. That's what DIIOC stand for. Injecting concretes as interfaces is key to making this happen. Your implementations can be easy to replace, and it allows you to write small unit tests. This is the steps to eliminate class-to-class coupling. Very simple. Next, skill 2, identifying library to library coupling. So if you're coupled library to library, this is also really easy to identify. Does library A depend on library B? If the answer is yes, it's coupled. Does library B depend on library A? Yes, it's coupled. And then the worst coupling is when you have a circular dependency, A depends on B and B depends on A, and you have to jump through hoops to even make that happen because, for example, Visual Studio, if you're in one solution, it'll prevent that from happening. But you can still get around that. You shouldn't, but it can happen. So, doing it better. Here's one example of depending on interfaces instead of concretes. What you can do is you can have an interfaces DLL. A.dll is the concrete, A.interfaces.dll is the interface implementation. By separating the DLLs, the interfaces from the concretes, you can actually replace how your code is used. Same with B. We have B.interfaces.dll and B.dll. A.dll could reference B.interfaces.dll. And we have an implementation, which is B.dll right here. That implementation, we could swap it with a B2.dll that implements B.interfaces.dll. So it allows us to make the concretes replaceable. Still coupled. Code can get more decoupled than this. All right, chain dependencies. This is what happens when you couple library to library. You get chained dependencies. You can have a big O problem when you start coupling libraries. If A depends on B and B depends on C, then A depends on C. That's what chaining means. So with library to library coupling, it can become, at worst case, big O of n squared. We don't want to be n squared. That's one of the worst big O problems. We just don't want to have so much coupling library to library. The coupling increases n squared. So for n libraries, any given library can be coupled to n other libraries, n times n or n squared. The other problem is that all apps that reference one of these libraries inherit that coupling. Why is this not a problem when we do app to library coupling? Well, app to library coupling can be big O of n, where if an app depends on n libraries, it only depends on n libraries. And that's where we want to get to. App should be able to choose the libraries it wants. And when you couple library to library, you're forcing an app to bring along your baggage. So, doing it right, decoupled, no interlibrary dependencies. So here we have a nice little diagram that shows your app. We're going to call it the composition root. The reason we're doing that is the composition root is usually your application root. It's usually where you compose all the objects and hook them together. It's a very important concept in dependency injection and inversion of control. If you're not aware of the composition root, I suggest you look up some books on dependency injection and inversion control. But until then, if you notice, there is no line connecting A.dll to B.dll. They are just not connected at all. But the composition root depends on both of them. That is doing it right. So, basic implementation steps in C# to remove library to library coupling. 1. Use interfaces. Use an interface that is not implemented in the library. Keep interfaces small. Implementation. Create concrete implementations only in the app or composition root. In the app or composition root, wire up the concrete to the interface, usually using an IOC container. So this is just an example of coupled architecture. Start trying to follow the arrows here. Just go ahead, give it a look for a second. It doesn't look good. This is actually not as bad as it could be. I've seen much worse. So, doing it right, decoupled architecture should look a little more like this. Yes, it would be perfect if we didn't have these dependencies, but certain libraries are going to have dependencies. I'm going to jump back to the previous slide so that you can see coupled, decoupled. Now, one of the things you might ask is, hey, there's more libraries here than there are here. That's true. And the reason that that is like that is actually on purpose. Usually, the app doesn't actually need half of these libraries. They're only dragged along because they're so hard coupled to some of the other libraries. But once you decouple that, those libraries that aren't needed don't show up here, and you end up with a smaller dependency chain as well as decoupling. One of the things I want to reiterate is to make this happen, one of the keys is that the implementations aren't always in the libraries. Sometimes the implementation should be in the composition root. All right, so lesson 2 summary, what we've learned so far. How to identify bad coupling. Most often problematic coupling is class to class and library to library coupling. What to do instead? For classes, you should only depend on interfaces. For library to library coupling, anytime a library depends on another library, you can identify it. What to do instead? Include unimplemented interfaces. Don't depend on other libraries. Let the app depend on the libraries, and also have the app implement some of those unimplemented interfaces. All right. So now we're going to actually get into the lab. Practical decoupling implementations. As you see, I have a link to a document right here. We're going to go ahead and click that and open that document. This document is how to prevent or remove coupled code. It's a Word document that goes through a lot of the same things we just talked about in this PowerPoint, has many of the same screenshots, many of the same explanations, and when it reaches the end, we get to a section of labs. We're going to go ahead and do these labs, and these labs are all on GitHub. We can go ahead and bring up this GitHub site, examples.decoupling. There's really nothing in the main branch. Every one of our labs is going to be a different number in the branches. So that's what we're going to be looking at. We're going to start with looking at coupled code, and I'm going to go ahead and just kind of demo this and bring it up in Visual Studio. I was able to check out the rias.examples.decoupling lab, and as you can see here, I have the first of the branches checked out, coupled code. This is a very, very simple setup. We have an a.dll in an A project and a b.dll in a B project. We have an A class and we have a B class. So A is just demoing an example coupling to B. So here you can see it is hard coupled to b.doSomething. And then in program, you can see that we create an A and we can call a.doSomething. Very simple. We can even go ahead and click to run our app. The window pops up and you can see that it called B did something and A did something. So as we click back on program, we can see here that we only created a new A. It's coupled to B and it's very hidden. Right here you can see one of the problems is that we have a hidden dependency on B. We don't even know it's there. In our composition root, we didn't have to create a B. So that's problem 1. Problem 2 is A will have to recompile. If I come here and I make any change to B, even if it's just a simple comment, and I save that, and I'm going to come up here to build and click build solution, my expectation is that only B builds. But as you can see from the output, it had to rebuild everything. All projects, both B and A, built just with a change from B. And so did the tests, and so did program. It created a build nightmare and a build dependency. Now remember, we were talking earlier, when does the dependency really become a problem? It's usually at build time, not at runtime. At runtime, this isn't the worst problem at all, but at build time, we have created a problem here. All right, we're gonna go coupled to C, and we'll continue to check that out. Okay, so now with coupled library C checked out, you can see it's the exact same dependency chain, just with an additional C. And you can see in A that we needed to create a new B and a new C in order for it to run. Once again, we have the same problem. Both B and C are hidden, and that's a problem. When we run it, we can still see that it called C did something, B did something, A did something. It definitely called all three of them, but again, C and B are hidden dependencies. And once again, if we come make some type of change to C and we want to click build and go look at our output, you can see once again, 7 built, 0 were up to date. It created a chain reaction that caused the entire set of projects to rebuild. It can affect us, it can slow down build times and cause lots of problems. So let's go ahead and jump to interface only library. What we have here is we still have an a.dll and a b.dll, but what we've done is we've created a.interfaces and b.interfaces. And that gives us a little bit more capability. We've also changed A to use constructor injection. We've now solved some of the problem. So if we look at program, constructor injection solved the problem of having a hidden dependency. We can now see A and B are both dependent. dependencies. Next, if you notice, A only depends on B.interfaces. It doesn't depend on B. I'm just going to go and click on output and show that we've already built these projects. But when I go ahead and come to B and I want to make some change and build, I can come look at output and 3 were up to date. It didn't create an entire dependency chain rebuild. However, it did still build more than we wanted it to build. 4 succeeded, 3 up to date. So we alleviated the problem a little bit, but we didn't completely solve it. So you can see having interface only libraries is a significant improvement and step up from having libraries only. And let's jump back to program.cs. If we run this, at runtime, nothing changed. It's exactly the same. This is a benefit for the developer. This is the benefit for the company to save money. The runtime is going to be identical. But because the developers are spending less time, they can have better unit tests, we can build less, we can compile less, we can use less build agents. It's a huge money saver on the engineering side. Notice we're still coupled to B.interfaces. It's not completely a decoupled scenario, and we want to get away from that. So as we jump to our third zero coupling, we're going to get away from that. Now in this branch, some of the key things I want to point out are A has no reference to B or B.interfaces. B is the same way. B has no reference to A.interfaces. It only references B.interfaces. Now the app does reference both A and B and their interfaces. As we go to program, we can see we're using dependency injection. We can create a new B, we can create a new A, and now we have something new called a concrete do something. This is what allows us to solve this problem. If we come look at A.interfaces, here in A, we know that some external system is going to want to do something. We want to make sure that all coupling to both IB and B is gone, which we have succeeded by creating an unimplemented interface. I do something event is sitting here. It's going to do something, it's not implemented, and when A actually wants to call do something, it's going to forward to the do something event and call do something. We've talked before about this being implemented in the composition root. So if we go to the app, we can see that concrete do something is implemented in the app or composition root. We've created a concrete do something and it implements I do something event. The app references B, so we're going to take in an IB and we're going to call B. Now if you look at this, we're going to create a B. B is going to be injected into the concrete create do something event, and the concrete do something event is injected into A, and by doing this, we've now decoupled both A and B. As you see, we can run, and once again, our application did not change at all. The runtime was completely fine. Everything we've done is for the engineer, to benefit our engineering department, to save money in our engineering department, to have decoupling, to improve developer speed, all about a better code architecture. So A doesn't depend on B. We can even see, if we come here to B, we can even change B.interfaces. We'll make some change here, and when we click build, you can see 4 were built, 3 were up to date. We're still in a better state, so we built B.interfaces, B.tests, and the app. If we change something just in B and build, you'll see that we only had 3 things build. B.tests, and the app. So we're minimizing the things that we build by this. This is going to save time with the build server. It's going to make development practices and your engineering department move faster. So this is zero coupling. A has zero coupling to B, B has zero coupling to A. Everything is wired up in the composition root in the app. Now, some of these other branches I'm going to leave for you to look at on your own in your own time. But what we want to really jump on is zero coupling with JSON serializer. All right, so we've now checked out branch 4, zero coupling with JSON serializer. It's the exact same architecture. We have A.interfaces, A.test, B.interfaces, B.test. Only instead of just do something, let's do a real implementation. We now have a third-party library. Our third-party library is newtonsoft.json. We want to be able to serialize something when we run. So now our runtime is different. What we're doing now is we're going to serialize each object we create and output it to the window. So we want to start with looking at A and look at the different architecture. A now takes in an iSerializer. Now that iSerializer, it is a serializer specific to A.interfaces, and it is injected in. However, notice there's no no concrete iSerializer implementation in A. No, that is left to happen in the composition root. We have multiple implementations for A. It's really critical that there is no implementation of iSerializer in A. And we can see the same architecture in B. B takes in an iSerializer. However, it's not taking in A's iSerializer. It's taking in its own iSerializer. This is pretty much a copy and paste. So we have two iSerializers, one for A and one for B. So the first thing a novice developer might ask is, why is this not breaking the dry principle? We have one responsibility to serialize, but yet we have two interfaces. Well, these actually are solving separate responsibilities. This is the serializer for library A and A.interfaces. This is the serializer for library B and B.interfaces. If we tried to put them in one library, then both A and B would have to be coupled to that library. And the whole point of this is to decouple. And the only way that we can decouple is for each to have their own very tiny serializer. And then, like we've talked about before, we put the implementation in the composition root. And here you can see that we've actually been able to create two implementations. For each, a serializer has a Newtonsoft.json implementation and a system.text.json implementation. Same with B. It's got two implementations. Now in the composition root, we can create all four of our implementations, two for A, one Newtonsoft, one system.text.json, two for B. Now we can create different instances of A. One can take in the Newtonsoft serializer, one can take in the system.text.json serializer, and same for B. So the benefit we've gained is there is no coupling on the serializer in either A or B. Now this might not sound awesome when you're talking about two libraries. We have library A and library B. It would be super simple to just have a third serializer library and make sure everything is coupled to that. And architecturally, something like that could make sense in your environment. But remember, that's adding coupling to a serializer library, which may or may not be the best solution for you. Hopefully you'd at least do a serializer.interfaces if you went down that route, and then they wouldn't be coupled to the actual serializer implementation. However, in this case, imagine if the implementation was Newtonsoft and you had 100 libraries and all 100 of them had to have a reference on Newtonsoft.json. That means every time you update Newtonsoft.json, you have to update it in 100 places. That's a NuGet package update. That check-in alone could be huge. Not to mention, if the decision is made that you want to replace Newtonsoft with system.text.json, now you have to go make a major code modification to hundreds of libraries. Yes, in this example, we only have two, but we are going to have hundreds of libraries in an enterprise application. So what we want to do is make sure that none of those libraries are coupled to a specific serializer, but each one of them can just have the serializer injected in. And that happens in the composition root. As you see, we're already able to replace the serializer in the app or the composition root. We're able to create different implementations and inject them in. And we can run this and see that. So here's the run. This first one uses Newtonsoft. The second one uses system.text.json. Same here, Newtonsoft, system.text.json. There's really no difference. Either of them can be used, but the point is that we should have a more decoupled architecture. Here's a diagram of two possible architectures. We have the recommended architecture 1 with zero coupling and the recommended architecture 2 interface coupling. In the zero coupling, the trade-off is that you're going to have big O of n concretes in the app. Each library that implements a serializer will have a concrete implementation of that interface. Down here, n libraries reference serializer. You'll have n coupling, but you'll only have one concrete. Your last lab, Lab 5, is to look for example in your own proprietary code base. Often logging is a good example. Create a new library or look at an existing library, but consider adding logging without referencing the library with the logger. Instead, have the app or composition root reference the logger. Just like we created an iSerializer, you could create an iLogger. Serialization might actually be a real example in your environment, but try and do a new one, maybe with logger or maybe with something else that's important to you. Thank you for watching this presentation on how to eliminate coupling.